So here's my matrix. I need to find the inverse of. Now we know what to do. I mean, we knew what to do before, but now we see the reasons for what we do. It is far better when we know the reasons for what we do. So we augment it. We augment this. That's my augmentation with the identity on the right-hand side. And now I start moving towards the row echelon form. I don't have the details of actual steps for the row echelon form because we practiced enough of that on Monday. And in fact, all these examples I'm about to show you about the inverses, they are quite heavy in terms of the amount of numbers you have to crunch. And sometimes the expressions you will see on the right-hand side, they will be relatively complex. It doesn't mean you don't have to do that. You do have to do those computations on your own. It just, what I suggest you do is you don't do it here in class. It will be very difficult for you to keep up. You will, I'm sure everyone here will revisit this content anyway. So when you revisit it in your own time, you will have a chance to double check all those computations. Right now, just focus on the principles which help me choose the row operations. And never mind the actual number crunching. The slides, they will be published. You can do it in your own time and double check every single arithmetic computation in those slides. But right now, let's focus on the process of selecting suitable sequence of row operations. So when you do this, there will be two parts, of course. First is a part when you go to the row echelon form. And this is a part which I don't have any choice because, like I said, we practiced on this on Monday. I'll just give you the what it is. This will be the row echelon form if you apply certain sequence of row operations to this matrix. And if you choose that sequence based on the experience you had on Monday, or you learned from the Monday lecture, 2 lectures on Monday. But this is not enough to actually to present the inverse, because after you reach the row echelon form, this is already a row echelon form. The second row has more zeros than the row above it. But this is not enough. We have to transform it further to what is called the reduced row echelon form. Only then we can claim the inverse. This extra transition, it aims to achieve precisely the identity on this side. I'm going to show you the row operations. Once again, don't really focus much on the number crunching. Focus on the choice, on the principles which govern my choices of the row operations. You can double check number crunching later. So we aim to achieve identity, and we start off with it backwards. So we try to achieve zeros above the diagonal, and we try to do it in a way that we move from the right to the left. So what I will do first, oh yeah, that's what I can do to achieve 0 in here, because I need to vanish everything above the diagonal. To some extent, you can make the following picture in your minds. Row echelon form, it's when we aim to make zeros below the diagonal. Reduced row echelon form is when we aim to make zeros above the diagonal. That's the second stage, the one we discussed right now. So I aim to make zeros above the diagonal, so I aim to vanish these two, and that's a very nice choice of the operation which will achieve that effect. Because -2 plus 2, it's 0. So the result of this, is this matrix. This is not yet an identity, but it's very close. The only thing which has to be changed is we have to scale out -2 from the second row. And that's my second choice of the operation. The moment I do that, I'll have a perfect identity matrix on the left-hand side, and that's where the process finished. This is the reduced row echelon form, and the left-hand side of that reduced row echelon form is the inverse of my original matrix A, I should say. You can quickly double check. I always encourage you to do the double check, because all of this is very intense, computation-wise. You may do a very minor computational mistake, and that will lead to the entire thing being incorrect. That will be very upsetting, but it's, like it or not, it's your fault. And you have to make sure, you have to have a safety mechanisms to make sure you don't do this. The best safety mechanism is a double check when you multiply your result with the original matrix and see whether that delivers identity. Let's just try it. If I try it this way, the result will be 2 by 2 matrix, and we'll just try to see what that will be. So in order to identify this component, I have to take first row here and the first column here. 1, -8, 2, and 9. -8 plus 9 is 1. So far, so good. Next one goes first row, second column. 1, take 1, 0. This row, it's a dot product. Second row in A and the first column in A inverse, proposed A inverse. 9, 16, 9 times -8 is -72. 16 times 9 on 2, it's again 72, so it's a 0, 1. And the final one is 9, 16, and 1, a half. So it's a 9 times 1 is 9, and 16 times -half is -8, so it's 1.